I talk about metric embedding via shortest path decomposition. Let's see how tree-like is a graph. So a tree decomposition of a graph G is a pair T and V, where T is a tree and V is a family of vertices sets. Is a family of vertex sets, Vt of G, and people say bags of decomposition. Bags of decomposition if for any V in V of G, the set TV, which is T where V is in Vt, is a non-empty subtree. For example, a tree decomposition could be like this: 6, 7, 8, 9, 5, 4, 3, 2, 1. And a tree decomposition is this. This is a tree decomposition. And these are bags. This could be a tree decomposition. But it could be also, I can say, a different example. For example, this one. This is a tree decomposition. But we have also a nicer tree decomposition as well. For example, if 1, 2, 3, 4, 5, 6, then I can say that this is a nicer decomposition. 4, 3, 1, 5, 3, 4, and 5, 6, 4. So now that you know what is a tree decomposition, so given a geodesic shortest path P, we can probabilistically embed all points into 2 dimensions with respect to P. For example, phi is an embedding into RD, and so we have a contraction. This is tau is a contraction, and we preserve the distances. So this ratio is not too far from 1. And this is the expansion. And you know, tau and rho could be greater than 1. So examples of LP norms are Euclidean L2 norm, or also cut norm L1. These are examples of LP norms. And when we say distortion, I mean tau rho. Tau rho is a good measure of distortion. And so let's see, there is a theorem. There is a theorem that says any graph with path phase K embeds into LP with distortion order of K to the 1 over P, where P is LP. So embeds a vertex relative to geodesic paths using two dimensions. So Arnold, in his nice article, he explained that we can embed like this. For example, of course, this is just an elementary thing that I will explain. I will explain his article specifically in details. And so this is delta 2. So this is your root of this path, this shortest path. And so you decompose it into delta 1 and delta 2. And delta 2 is d of v and r. So we have v. What is the distance between v, this v and root? And what is the distance between v and this path? So these are your coordinates. The motivation is that Bourgain says, I know that for every endpoint, metric x and dx, it is embeddable into LP with distortion order of log n. So do you say that you want to be even better than this? We say that, okay, Bourgain, your theory is very nice, but for some special cases, for example, tree, path-width tree, and we can say that, for example, path-width graph, for example, tree depths, tree-width graph, bounded tree-width graph, or bounded path-width graph. For cases like this, we can say that because it's a special case, we can make it tighter. So the embedding has, you might say, that what is your embedding? So the shortest path decomposition So given a weighted graph, a shortest path decomposition of depth k is a pair, where x is a collection of partial partitions, and p is a collection of sets of paths. For example, this is path 1, this is path 2, path until path k. And so for every I between 1 and k, and every subset x in xi, there exists a unique path px such that px is the shortest path. And also for every I, xi consists of all connected components of g, x exclude px over all x. So what does it mean? Before talking about the meaning of that, let's see the relationship between two seemingly simple and similar ideas. In sparsest cut problem, if S is a subset of V, we define the sparsity by phi of S, edge of S and S bar, cardinality F, S and cardinality as S bar. You know everything about this sparsest cut problem. Okay? The interesting thing I want to notice, I want to point out that finding the cut with minimum sparsity, everybody knows that it is NP hard. But I want to relate two different things. G embeds into L1 of RD with norm 1 with distortion T. Solving this problem is like solving T approximation for sparsest cut, and there are many articles about this fact. So can we have lower distortion than Bourgain? I said that we can talk about special cases. For example, the first special case is bounded treewidth graph. The second special case is bounded path with graph. And you know the tree depths of a tree decomposition is the size of maximal bag minus 1. For example, in this example, these are in one bag, these 3 vertices are in another, these are on another bag, and then you have final bag. For example, here the tree depth is 2 because 3 minus maximum size of bag is 3. This is 3. So 3 minus 1 is 2. Or I can say an example of path-width graph, a tree which is a path like this, and they are separated like this. It has 2 shortest paths. One shortest path is like this, for example. If we remove the first shortest path, then we only have 2 shortest paths. So we define G has an spd shortest path decomposition depth of K if after removing some shortest path P, every connected component in G excluding P has a spd of depth K minus 1. For example, tree width K has a spd depth of order K log n. Path width K has a spd depth of K plus 1. There is a theorem that says that the theorem says if G is a graph, be a weighted graph with an spd of depth K, the article of Arnold, he proved that then there exists an embedding V to LP with distortion just K to the minimum of 1 over P and 1 over 2. Arnold proved this interesting theorem with construction. So not only existence, but also explicit construction that can be used for applied purposes. So the idea is removing shortest path induces a hierarchical partition. So the embedding will be defined recursively using different coordinates for each cluster. For example, if this is a path, then we can, if we just remove this path, we have two different clusters. We have 2 different clusters. So if I just find another shortest path like here, we can decompose it more. So recursively we can create other clusters. And then we recurse. And this continues forever until we find the smallest granularity. So this guarantees that consider U and V in V, we want to guarantee that for every coordinate, if we could be able to say that this guarantee holds, then we are done and our embedding satisfies a good distortion, a very small distortion. So this is the first one is the Lipschitz condition. And the second one that it says that there is some coordinate such that fi of v minus fi of u is dg, v, and u. So each vertex is non-zero only in k coordinates. I mean the cluster that it belongs to. And because the number of coordinates may be very huge. So let's see this in action. That, as I said, we have a path, we have a vertex, the minimum distance between that and the path is delta 1, so this is the first coordinate, d of v and path, and delta 2 is the distance between v and root, so this is the root of this path. Okay, so points far from the path, this is the path, and so we have cluster x1 and x2. Then the first coordinate is to the path. So it's if u is here, this is delta 1. If v is here, another point, it is delta 1 is here. So you see, so points that are far from path, it becomes delta 1 of u plus delta 1 of v. So you can say that d of u and p plus d of v and p satisfies what I said in my previous slide. And there is another case, is that points that are close to the path. For example, this is the root of this path P, and it creates two clusters, x1 and x2. And we say that this is point V and delta 2, and this is U delta 2. And here you can say that delta 2 of U minus delta 2 of V is du of R and dv of R. So it is a constant order of dg, u, and v. So we use different delta 1 coordinate for each component, and we use the same delta 2 coordinate for all components. The problem is that expansion is unbounded. It means that if we have a path and we have v here, u here, very close to the path, and then we have a path here, we have a shortest path here. This distance is delta 1 because it is to the path, and this distance is delta 2 because root is here. And you know what happened if dv and p and dv and rv, those distances are very, very greater than v and u. So we embed with respect to only current clusters, so these problems is like this. But to avoid unbounded distortion in future levels, we truncate. It means that, okay, so we have a boundary as well. And if this is the boundary, for example, this is x, this is p, this is your point, and this is delta 1, which is d of v and path, delta 2, which is d of v and your root is here. And the boundary, the minimum distance between this point and the boundary is this. So the minimum distance between v and outside, which is v but not x, is this. So for each v in the cluster, both delta 1 and delta 2 will be truncated by this dv, v and x. So we make sure that there is no unbounded distortion. But we have another problem, so if this is R and this is X,